Okay, you just read and took notes on 2-4. So let's talk about some of the specifics, especially for the AP test related to constant acceleration. And just a reminder how this relates to the graphs. We're talking about situations where the position time graph is quadratic, that the velocity time graph is linear, and therefore the acceleration graph is a flat line. Not zero, but a flat line at a positive or negative value that does not change as time goes by. Okay, so we are going to look at the AP sheet of, so if you were going to take this test on paper, you would see this at the beginning of the test section. You would have your constants printed, and then on the next page you would have your formulas, and right at the top the first three equations give you these equations of motion for objects that have constant acceleration. You cannot use these if acceleration is not constant. And they're for objects that are moving in one dimension, they're going to use the x here. But we are going to use these even for situations when things are moving straight up and down, like along what you would normally call the y-axis, right? Okay, so let's talk about what these variables mean. We have x, meaning x as a function of time, x of t. X0 means where was this thing when time began, when time was equal to 0. Vx is v of t, is the way we have been using it. V0x refers to how fast it was moving at time 0, or velocity at time equals 0. Ax is referring to the acceleration, and then time. Sometimes I slip up and put delta t because that other book uses that. So we can use the delta, or we can just put elapsed time. How much time has gone by between time equals 0 and now. Okay. And then I thought we should talk about this kind of question. Okay, where it's asking you to analyze a situation given the equation for the motion. And because we just studied that equation, we know what these variables mean. So if I rewrite that first equation up here, I have x equals x0 plus v0x t plus 1/2 ax t squared. Okay, and let's take these options one at a time. The object starts to the left of the origin. Well, that would mean that, another way to say that is x0 less than 0? Left of the origin means a negative number. And when we talk about the position relative to the origin, that's really talking about x. Okay, well, if I look at this value of 2 meters, that's a positive number, so that's to the right of the origin. Okay, that one's out. The object starts with an initial velocity. Well, that's referring to v0x. And if I go looking for the coefficient that corresponds to v0x, I see a 0 there. So it began with 0 velocity, not some other number. So this one is out. Okay. The object has a constant velocity. That would refer to a situation when ax is 0. That way that whole term would go away and the velocity wouldn't change. But but that's not the case here because we clearly see that whole third term with AX involved, where here's AX, right? So we know that's involved here. So that's not it. It's got to be number 4, but let's check. So supposedly this object would be speeding up. Now, in the past, we've talked about how if something's speeding up, the velocity and the acceleration would either both be positive or both be negative. But we know that this object has an initial velocity of 0. So what about when you start from 0 velocity? Then in the acceleration, we know the acceleration is negative. So then what's going on with that? Well, one way to think about it would be we could do the velocity function and look at that. We could draw that. We could make a t-chart. So if we take the first derivative, we would get Vx equals V0x plus AXT, right? If you do that generically, you take the first derivative. This is t to the 1, so I take that 1 down here times V0x. Then all I'm left with is V0x t to the 0. And then I bring this 2 times this 1/2. I get just 1 AXT. Wow, that's where that comes from, is the power rule and the first derivative of that position function. So then the position function for this situation would be, I have 0 here plus -1 meter per second squared, t. So then my Vx function, if I graph it, I should have left myself more space. I'm starting at 0 and I'm graphing a line that goes down like that. So then for sure I'm going to get something that speeds up. It's just speeding up in the negative direction. Okay.